will discuss the homotopy types of certain spaces related to the sphere. Okay, so this picture here, it shows a sphere, but we've removed the North Pole. This little point marked in green is the North Pole, and we're removing it from the sphere, and we want to understand the remaining space. Well, if you can take the rest of the sphere, we can just shrink it back. You can pull it back away from the North Pole. If we'd left the North Pole in, then this process would kind of create a discontinuity at the North Pole, but because we've taken the North Pole out, that doesn't happen, and we can just shrink it, pull everything back all the way down to the South Pole, like so. Okay, so the conclusion is that if we take the we take a sphere and remove the North Pole, then that's just homotopy equivalent to a single point, or in other words, it's contractible. Another way to say that, I mean, we already had a look at this stereographic projection homeomorphism. So that shows that if we take the sphere and remove the North Pole, then that's actually homeomorphic to the plane R2. And the plane R2 is certainly contractible by a straight line homotopy. So that's another way to see that a sphere with one point removed is contractible. Okay, so now let's see what happens if we remove 2 points. We're going to remove the North Pole and the South Pole. And notice actually that if we, two discrete points, that's actually a zero-dimensional sphere. Right? The zero-dimensional sphere is vectors of length 1 in R to the 1. And so in R to the 1, the only vectors of length 1 are just +1 and -1. So your S0 just consists of 2 discrete points. So we can think of this, removing the North Pole and the South Pole is like removing a copy of S0 from S2. And if we do that, well, we can, because we've punctured the North Pole, we can shrink away from that. And because we've punctured at the South Pole, we can shrink away from that. And we can pull everything else onto the equator like this. Everything else just pulls back onto the equator. So the conclusion from that is that the sphere with 2 points removed is actually just homotopy equivalent to the equatorial circle. S2 with S0 removed, homotopy equivalent to S1. And here's a similar thing we can do. Instead of removing an S0 from S2, we can remove an S1, remove a circle. So the circle we're going to remove is the equator. So here we've marked the equator in green. And if we remove the equator, then we can pull everything else either up to the North Pole if it starts in the Northern Hemisphere, or down to the South Pole if it starts in the Southern Hemisphere. So the message from this is if we take S2 and we remove S1, then what we're left with is just the two, consists of the 2 poles, which is a copy of S0. So we're saying that if you take S2 and remove S1, that's homotopy equivalent to S0. In fact, there's a kind of more general thing. If you take S to the P and you remove S to the Q, then that's homotopy equivalent to S to the power S to the dimension P minus Q minus 1.